These two graphs show the same object moving over 10 seconds. From the graph on the left, we can see that at 5 seconds, the velocity is 0. However, the acceleration is still positive. Looking at the graph on the right, we can see that the object slows down, changes direction, and then speeds up the other way. Understanding how position, velocity, and acceleration connects and how these graphs show the same information is essential for Physics 1. In this video, I'll show you how to read both position versus time and velocity versus time graphs, and all of the information that we can glean from these two graphs. All right, let's start with the position and time graph. Let's look at that in more depth. On the horizontal axis, we have time measured in seconds, that's the S, and on the vertical graph, we have position measured in meters. Let's say that you have an object that moves, we'll say 6 meters in 3 seconds. So here's 3 seconds, 6 meters, and let's say that it moves with a constant velocity. So just a straight line between those 2 points. At 0 seconds, the position is 0 meters. So that's this point here. At 1 second, so over 1, the position is 2 meters. 2 seconds is 4 meters. And then 3 seconds is 6 meters. You can see that this position time graph tells us where an object is located at each moment in time. We can also use this to find the velocity of the object. And in order to calculate the velocity, we find the slope of the graph. Perhaps you've seen the equation for slope of a graph before, but if not, I'm going to write it up anyways. It is, let's see. It is y2 minus y1 over x2 minus x1. In our case, our position is the y values and the time is the x values. So you could also say delta x, which x is what you normally use to denote position, over delta t. So change in x over change in time. So this is going to be 6 minus 0 divided by 3 minus 0. So again, this is just the ending position value, the beginning position value, and then the ending time value and the ending, or the beginning time value. And if you calculate this out, you get 6 divided by 3 equals 2. Now, the change in x, the position, has units of meters, and the change in time has units of seconds. So we end up with 2 meters per second. This gives us that it is a constant velocity over this whole graph, a constant velocity of positive 2 meters per second. All right, let's look at another example. Let's say that you have an object that starts at 0 seconds, it's at 4 meters, and then over at 6 seconds, it's still at 4 meters, and it doesn't move between that time. So it just stays there at 4 meters. In this case, using this equation yields, well, let's see. We have 4 divided by 6. So beginning, or the ending x value and the ending time value minus 4 minus 0. You can see 4 minus 4 is just 0 over 6. And so the velocity is 0 meters per second. In other words, it doesn't move over this whole graph. Now, something else that's important to realize is, let's say we have something that, does this with position, where it's going forward, it's going backwards. Our average velocity, if we use this equation still, would still be 0 meters per second. So the average velocity over the whole travel time of this object is 0 meters per second. Let's look at one final example where we have a negative velocity. So let's say we start at, let's just do 4 again, and we go down to 0 meters at 4 seconds. So in this case, we have 0 minus 4 for our position, and then 4 minus 0 for our time. We end up with negative 4 over 4, which simplifies to negative 1 meters per second. So in this case, we again have a constant velocity averaged over this time. And in this case, it is negative because the position is decreasing. It's getting closer to 0. Let's return to our initial position time graph. You can see now that at every point along the graph, there's a different slope. So let's say we take this point right here. Slope is going to be like that, and it's pretty steep there. But if we take this point instead, the slope is a little less steep. And then the point at the very bottom, the slope is, choose a different color. The slope is 0. So our velocity at the very bottom is 0 meters per second, and then it gets a little faster and a little faster as the graph widens out. And we can't use our other equation to calculate that. In order to calculate the exact velocity at these times, you would need the derivative. And we will get into that later. But the important thing to remember is that a positive slope equals a positive velocity. Zero slope equals zero velocity. And then a negative slope equals negative velocity. And then the steeper the slope, the greater the velocity magnitude. And a changing slope, so like at this point right here, means that the velocity is changing. So in that moment, the velocity is changing from negative to positive. Let's move on now to velocity time graphs. On the horizontal axis, we still have time in seconds, but now on the vertical axis, we have velocity in meters per second. Let's say that you have a velocity of 4 meters per second, and it's a constant velocity. So 4 meters per second, it's constant, so it just goes in a straight line across everything. The slope of this line is 0 meters per second because it's flat or horizontal. The slope of velocity is going to be acceleration. So remember that slope of position is velocity, and the slope of velocity is acceleration. So in this case, we have a velocity, so a speed of some sort, 4 meters per second. But even though we have speed, we do not have any acceleration. You can think of it as if you're driving your car on the highway and you set it to cruise control at 75 miles per hour, and it just stays at that 75 miles per hour. It is not accelerating or decelerating. So even though it still has speed, it still has velocity, it's not changing in that velocity, and so the acceleration remains 0. If we look at our initial graph for velocity, I have it up here actually, we have a constant slope going from -5 to +5 meters per second. So we do 5 minus -5 divided by 10 minus 0. 5 minus -5 is 10, divided by 10 equals 1 meters per second squared. And this would be our acceleration. And the meters per second squared comes from velocity on top, which is meters per second, and time on the bottom, which is seconds. So you end up with meters per second times 1 over seconds, which is meters per second squared, which is the unit for acceleration. So our acceleration in this case is a constant of 1 meters per second squared. If you pretended for a moment that the graph on the right was a velocity time graph instead of a position time graph, we would end up with a changing acceleration similar to how we ended up with a changing velocity earlier. You can also have a constant negative acceleration. If your velocity graph looked like this, you would have 0 minus 6 divided by 6 minus 0, which simplifies to negative 1 meters per second squared, or a constant deceleration. So a constant acceleration of negative 1 meters per second squared. You can see now how you can connect these three graphs. Thank you again for watching this video. In the next one, we'll use the relationships we learned between position time graphs and velocity time graphs to introduce constant acceleration equations and solve full kinematic problems step by step.